Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This is the fourth video in a playlist on statistical tests. The video is about the chi-square test for independence. You can see here the others in this playlist that I have completed or plan to do. If you're not familiar with the chi-square as a test statistic, you may want to view my video, Chi-square the test statistic and its distributions, before viewing this one. And if you'd like to see the latest status of all my videos, completed and planned, you can find that at statisticsfromatoz.com/videos. As usual in the book and in these videos, we'll start by going quickly through a list of keys to understanding, or KTUs. This will end with the highlights of the concept on a single page. And then we'll go into detailed explanations of each of the keys. There are 4 keys to understanding the chi-square test for goodness of fit. The first key tells us that the test statistic chi-square can be used to test whether 2 categorical, also known as nominal or attributes variables, are independent or whether they are associated. KTU number 2 says, if 2 categorical variables are independent, then the observed frequencies of the different values of the variables should be proportional. Key number 3 says, using a contingency table, calculate the difference between the observed count and the expected frequency for each cell. The test statistic chi-square then distills all this information into a single number. Chi-square equals the sum of O minus the E squared divided by the E. The fourth and final key to understanding tells us that the test then uses the appropriate chi-square distribution to calculate chi-square critical and P. The null hypothesis is that there is no association, that is, the variables are independent. And here on one page are all 4 keys to understanding the concept of the chi-square test for independence. You may wish to pause the video at this point and read them all together. Okay, now let's take an in-depth look at each of the keys to understanding. KTU number 1 says, the test statistic chi-square can be used to test whether 2 categorical variables are independent or associated. Categorical variables are also known as nominal or attributes variables. We'll spend some time explaining all these terms. First, a categorical variable is one whose values are names of categories. This concept was explained in the previous video, and here's another explanation that may help. This table has 2 categorical variables, gender and ice cream. The first categorical variable, gender, has 2 values. Its values are the category names, female and male. The second categorical variable, ice cream flavor, has 3 values, the category names chocolate, vanilla, and strawberry. Categorical variables are classified as non-numerical variables because their values are names, not numbers. However, we get numbers by counting items within the categories. In this table, count data are recorded for each intersection of categories from the 2 variables. For example, at the intersection of the female column and the chocolate row at the upper left, there were 60 people who were both female and who preferred chocolate. And at the intersection of the male column and the strawberry row at the lower right, it shows that there were 50 people who were males and who preferred strawberry. Two or more variables are independent of one another if there is no relationship, association, or correlation between their values. For numerical variables whose values are numbers, correlation is the opposite of independence, and there are a number of types of correlation analyses available. For categorical variables whose values are names, the term association is used instead of correlation. And the chi-square test for independence is used to determine whether or not there is a statistically significant association. Here's an example of independent variables. Gender and day of birth are independent. There is not a higher or lower proportion of males born on Mondays versus Thursdays, for example. And here is an example of variables that are not independent. They are associated. The two variables are gender and type of clothing worn. Many more females wear skirts than males do. Independence or association is determined between variables, not between values, category names of the variables. In this table, the categorical variables are gender and ice cream. So we will determine whether ice cream preference is independent of gender or whether ice cream preference is associated with gender. The categorical variable gender has two possible values, female and male. The counts by gender are shown in the vertical columns. The categorical variable ice cream flavor has three values being tested, chocolate, vanilla, and strawberry. The counts by ice cream are shown in the horizontal rows. We are trying to determine whether the preference for an ice cream flavor is associated with a person's gender. For numerical variables, correlation is the opposite of independence, and there are a number of types of correlation analyses available. For categorical variables, the term association is used instead of correlation, and the chi-square test of independence is used. And the two variables are either independent or they are associated. Key number 2 says if two categorical variables are independent, then the observed frequencies of the different values of the variables should be proportional. In the first few tables shown here, frequency means the same as count. Later we'll be doing some calculations which result in non-integer frequencies. In this example, there are two categorical variables, gender and juice preference. The variable gender has two possible values. The category names male and female are the two possible values for the variable gender. The categorical variable juice has three possible values. The category names apple, grape, and orange are the three possible values for the categorical variable juice. Our question is, are the variables gender and juice independent? Put another way, does your gender have no effect on your choice of fruit juice? And you may recall that our key to understanding number 4 says that the null hypothesis says there is no association. More on that later. Let's say we surveyed 80 females and recorded their juice preference in the table below, or the table shown. This is the beginning of the contingency table. It is so named because we're trying to determine whether the counts for the two categorical variables, e.g. Juice, are that is dependent on the value of the other variable, example, gender. If gender has no effect on fruit juice preference, that is, if these two categorical variables are independent, then we would expect that the preference for males would follow a similar 35%, 15%, 50% pattern. And in this artificially simplified example, that is exactly what we get. We surveyed 40 males, which is half the number of females surveyed, and the counts for men are exactly half for those for women, for all three juice choices. So there is no difference between the fruit juice preference for women or men. Thus, the choice of fruit juice is independent of gender. Now, let's do a study of ice cream flavors. We surveyed 100 women and 80 men. You can see these numbers in the bottom row, totals. Now, one nice thing about this chi-square test is we don't have to have the same sample sizes of test subjects as we're showing here in this example. Clearly, females preferred chocolate by a wide margin, while males strongly preferred strawberry. So the categorical variables gender and ice cream preference are associated. They are not independent. Most of the time, however, things are not so clear-cut. What if the proportions in the gender juice contingency table were not the same but were close? How close is close enough? We need to use the chi-square test of independence to determine whether the differences in the proportions are large enough to be statistically significant. If so, the variables are associated, not independent. For fruit juice, we saw that the proportions were close, in fact identical, so gender and fruit juice are independent. For ice cream, the proportions are very different, so gender and ice cream are associated. KTU number 3 says, using a contingency table, calculate the difference between the observed count and the expected frequency for each cell. The test statistic chi-square then distills all this information into a single number. In previous examples, the data was very definitive. We could just look at the numbers and be pretty sure what our conclusion would be. Much more often, the differences are less clear, and we need the chi-square test to tell us whether or not the differences are statistically significant. Here is the formula for the chi-square test statistic. For each cell, subtract the expected value from the observed value, square it, and divide by the expected value. And the sum of all these values for all the cells gives us the value of the chi-square statistic for the test for independence. Important, the expected frequencies in each cell must be 5 or larger. Otherwise, our sample size is not big enough to conduct the test, or our categories are defined too narrowly. In our gender juice example, the proportions were identical for female and male. That is, of course, not usually the case. Let's say a cafeteria offers a choice of fish, meat, or vegetarian meals. Is the choice of meal influenced by gender? We collect the data shown in this table. These are the observed counts. Our sample has observed counts for 90 males and for 190 females and 100 males. We can see one obvious difference between the genders. The first choice was vegetarian for females and meat for males, but both genders chose meat over fish. And the picture is complicated by the fact that there are different total numbers for the two genders. So unlike the previous examples, we can't answer our question just by eyeballing the numbers. We need to run a statistical test, and that test is the chi-square test for independence. The question is, how likely is it that we would get these numbers if there were no difference associated with gender? That is, if the two variables were independent. It's a question of probabilities, so we can make use of the multiplicative law of probability. The probability of both of two things happening is the product of their individual probabilities. And we use this law to calculate the expected probability of each cell of data in our table. In practice, we'd have statistical software do this for us. In our table of data, each cell is the count of two things being in place. For example, the upper left count represents 26 females who selected a fish. Each of these two things, female and fish, have their own probabilities. The probability of female is the total count of females, that is 90, divided by the count of people polled, which is 190. 90 divided by 190 gives us 0.474. This is the probability of the female column. It is shown at the bottom of the female column in this table. The probability of fish equals the total count of fish choices divided by the count of all choices, that is 58 divided by 190. Note this is the probability of the fish row. It is shown at the right of the fish row. Therefore, the probability of a female who chose fish is the probability of a female, which is 0.474, times the probability of fish, which is 0.305. This gives us 0.145. This is our expected probability for female and fish. We'll enter this into the first table on the next slide and calculate the other numbers in a similar fashion. The expected probability of each cell in the top table is the product of the probability of its row times the probability of its column. This table shows us the probability for each combination of gender and meal. In the upper left white cell, we can see the 0.145, which we calculated for female and fish. Next, for each cell, we multiplied the expected probability by the sample size for all our data. This is shown in the bottom table. This gives us the expected frequencies for each cell. You may wish to pause the video here to take a closer look at the numbers. The expected frequency is what we could expect to see if the variables were independent. Note that frequencies do not need to be integers as counts do. Remember, we said earlier that each expected frequency must be at least 5 or larger. And we see that all our expected frequencies easily meet that requirement. It's important, although within the calculations there are comparisons of proportions, do not convert the count data to proportions or percentages before entering the data into the table and doing the calculations. Count data contains information on the sample size, and that information is lost when you convert to proportions. Likewise, do not round the count data. Here again is the formula for chi-squared when used in a test for independence. For each cell, subtract the expected value from the observed value, O minus E, square it to make it positive, O minus E squared, and divide by the expected value, O minus E squared divided by E. Then sum up all these values for all the cells to get the value for the chi-square test statistic for this test. Chi-squared distills the information and all the data values in the sample into a signal number. This value for the chi-square test statistic summarizes how much the sample varies from one which would have independent variables. This formula makes it clear why a large difference between O and E results in a large value of this chi-square test statistic, and a larger value for the chi-square test statistic is more likely to be greater than the critical value, and thus it is more likely that the variables are associated and are not independent. It also explains why this test is always right-tailed. Only large positive values of chi-square are in the extremes beyond the critical value. Following the formula, we get a value for chi-square which summarizes the data and how it differs from what we would expect if the variables, gender and meal preference, were independent. In our example, chi-square equals 5.24. KTU number 4 says, the test then uses the appropriate chi-square to calculate chi-square critical and P. The null hypothesis states that there is no association, that is, the variables are independent. If we were doing a hypothesis test, we would have stated a null hypothesis along with selecting a value for alpha before collecting the sample data. A null hypothesis, H sub 0, usually states that there is no difference or no change or no effect. In this test, we can view it as saying that the values of one variable have no effect on the counts in the other variable. The test then uses the appropriate chi-square distribution to calculate chi-square critical and P. Again, the null hypothesis states there is no association, that is, the variables are independent. There is a different chi-square distribution for each value of its degrees of freedom. For a contingency table with R rows and C columns, we calculate the degrees of freedom as df equals R minus 1 times C minus 1, where R is the number of rows and C is the number of columns. In our meal preference example, df equals 3 minus 1 times 2 minus 1, and it equals 2. As we explained earlier, the test is right-tailed. For a right-tailed test with df equals 2 and alpha selected to be 0.05, the critical value, chi-square critical, is 5.99. This number can be found in reference tables or calculated via software. In our example, the following table is how one software package summarized the results. As we explained earlier, the test is right-tailed. For a right-tailed test with df equals 2 and alpha at 0.05, the critical value chi-square critical is 5.99. Now this can be calculated via reference tables or via software. Now chi-square is less than chi-square critical, and equivalently p is greater than alpha, so we fail to reject the null hypothesis of no association. We conclude that there is no association, so the variables gender and meal preference are independent, as this table states in the lower right. Now you may have noticed that the f expected and m expected numbers in this table differ slightly from the expected frequencies table we calculated earlier. That is because in the tables shown earlier, we rounded several times in order to display interim numbers and avoid showing overly long strings of decimals. This graph is a close-up of the right tail of the chi-square distribution. The shaded area representing alpha is sometimes called the rejection region, and the white area is called the acceptance region. We can see that chi-square is in the acceptance region. That concludes our discussion of the chi-square test for independence. This has been the 5th video in a playlist on statistical tests. Coming next are a video on the 3rd kind of chi-square test and a video on non-parametric tests. You can always check the videos page on my website for the latest status of videos completed and planned. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip of the week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z.